morning to all of my students. Myself, Mr. Dibyendu Mondal, Assistant Professor of Mechanical Engineering Department of Greater Kolkata College of Engineering and Management under JIS Group. In this pandemic situation, I am delivering my lecture through online mode and my video is uploaded in YouTube. Good morning. Today I am discussing about approximation of isothermal compression. Although isothermal compression is economical, it is not possible to achieve it in practice. To have an isothermal compression, the compressor will have to be run extremely slow, while in practice it is driven at high speed so that as much air as possible is compressed in given time. Since there is savings of work by compressing air isothermally, it is necessary to make an attempt to obtain approximately an isothermal compression. These methods are adapted to achieve this object while still running the compressor at high speed. The three methods adapted are cooling the air during compression by spraying cold water into the cylinder, cooling the air during the compression by circulating cold water through the cylinder jacket, adopting multi-stage compressor with inter-stage cooling. Cold water spray. Cold water spray. In this method, cold water is sprayed into the cylinder during compression. The cooling thus done reduces the temperature of the air and the compression curve will be approximately of the form Pv to the power 1.2 equal to constant. This means that the compression is brought nearer to isothermal, which result in the savings of work. Water jacket. In this method, the heat of compression is extracted by circulating cold water in the cylinder jacket, thereby keeping the temperature rise as small as possible. This keeps the compression near to isothermal. Multi-stage compression. In this method, the compression of air is carried out in two or more stages in separate cylinders. The pressure of the air is increased in each stage. It is common practice to provide intercoolers between the cylinders of multi-stage compression. For the purpose of cooling the compressed air to atmospheric intake temperature before entering the succeeding next stage. It is this cooling between the cylinder that keeps the compressor very near to isothermal as shown in this figure 11.6. Okay, combined identical indicator diagram for two-stage compression with perfect intercooling. Okay. In figure this combined ideal indicator diagram for the low pressure and high pressure cylinder of a single acting two-stage air compressor. Okay, arrangement of cylinder, indicator diagram of HP cylinder, indicated diagram of LP cylinder. Two-stage air compressor with intercooler. Okay, pressure versus volume. PV to the power n is equal to constant. Okay, combined ideal indicator diagram. One is the actually polytropic process. PV to the power n is equal to constant, parabolic in nature. When n is equal to 1, PV is equal to constant, and when n is equal to infinity, pressure is equal to constant. Arrangement of cylinder. This is the arrangement of cylinder indicator diagram. This is the diagram, indicator diagram of HP cylinder, indicator diagram of LP cylinder. Combined identical indicator diagram, two-stage compression with perfect intercooling. The low pressure cylinder diagram is shown here, and the high pressure cylinder diagram as P2 to 3 P3. The reduction of work required due to intercooling is shown by the shaded area 2, 3, 3 prime 2. When cooling is perfect, that is when air is cooled to intake temperature in the intercooler, T1 is equal to T2. The point 2 will lie on the isothermal line 1 to 3 as shown in figure. It may be noted that each stage will increase the pressure of air while the intake temperature T1 is maintained same at the end. The isothermal line during the process has been approximated as shown by the diagram in the shaded area. Okay. Actually, imperfect intercooling, figure 11.7 represent the indicator diagram of a two-stage air compressor with imperfect intercooling. Let the compressor follow the law PV to the power n is equal to constant, and the intercooling be incomplete, so that the point 2 has not reached the isothermal line, that is, point 2 does not lie on the isothermal curve. Let P1 is equal to PA Newton per meter square and V1 is equal to in meter cube represent, and V2 represent the condition of air entering high pressure cylinder, and P3 be final delivery pressure of air. Then the total work done for compression and delivery of air per cycle will be the sum of the work done in each cylinder. Work done in LP cylinder as shown in the figure. So the savings of work done due to imperfect intercooling is shown by the shaded area 2, 3, 3 prime 2. So that is the shaded area 2, 3, 3 prime and 2. Work required in LP cylinder per cycle n by n minus 1, P1 V1, P2 by P1 whole to the power n minus 1 by n minus 1. So that is the work required in LP cycle, LP cylinder per cycle n by n minus 1, P1 V1, P2 by P1 whole to the power n minus 1 by n minus 1. Work required in HP cylinder per cycle n by n minus 1, P2 V2, P3 by P2 whole to the power n minus 1 by n minus 1 joule. So the total work required per cycle W is equal to n by n minus 1 P1 V1 P2 by P1 whole to the power n minus 1 by n minus 1 plus P2 V2 P3 by P2 whole to the power n minus 1 by n minus 1 joule. So indicated power of the compressor, that is equal to Wn by 60. N is equal to number of cycles per minute RPM for single acting compressor, and W is the work required in joule per cycle. P1 V1 and P2 V2 in the equation are substituted by MRT1 and MRT2 respectively. Then work done per kg of air can be written as W equal to n by n minus 1 at T1 P2 by P1 whole to the power n minus 1 by n minus 1 plus at T2 P3 by P2 whole to the power n minus 1 by n minus 1. If the compression is isentropic, gamma should be substituted for n in equation, and another one is the perfect intercooling. If intercooling is perfect or complete, the point to lie on the isothermal line. That is, point 2 will coincide with point 2 double dash. Then P1 V1 is equal to P2 V2. Substituting this in equation, this one W is equal to n by n minus 1. P1 V1 P2 by P1 n minus 1 by n plus P3 by P2 n minus 1 by n minus 2 joule. So indicated power of the compressor, that is equal to W into n by 60 joule per second. Actually the joule per second, that is equal to watt, where n is equal to number of cycles per minute equal to RPM for single acting compression. W work required in joule per cycle. If P1 V1 in equation is substituted by MRT1, the work required per kg of air may be written as W equal to n by n minus 1 at T1 P2 by P1 n minus 1 by n plus P3 by P2 n minus 1 by n minus 2 joule. Indicated power of the compressor, W is equal to mass of the air delivered per second, joule per second or watt. So W is equal to work required in joule per kg of air, heat rejected to the intercooler per minute, mkp T2 prime minus T2 kJ. So m is equal to mass of air compressed per minute, kp is equal to specific heat of air at constant pressure, T2 prime temperature of air before entering the intercooler, and T2 temperature of air leaving the intercooler. Okay. Another one is the ideal indicator, ideal intercooler pressure. It may be noted from the figure 11.6. This one. The point 2 will lie on the isothermal line. That is, point 2 will coincide with point 2 prime, 2 double prime. Then P1 V1 is equal to P2 V2. Substituting this in equation, total work required per cycle, W is equal to n by n minus 1 P1 V1 P2 by P1 whole to the power n minus 1 by n plus P3 by P2 whole to the power n minus 1 by n minus 2 joule. Indicated power of the compressor, W into n by 60 joule per second. N is equal to number of cycles per minute. equal to RPM for single acting compressor. W is equal to work required in joule per cycle. If P1 V1 in equation is substituted by mRT1, then work required per kg of air may be written as W is equal to n by n minus 1 RT1 P2 by P1 whole to the power n minus 1 by n plus P3 by P2 whole to the power n minus 1 by n minus 2. So, indicated power of the compressor W into mass of air delivered per second, joule per second or watt. W is equal to work required in joule per kg of air. Heat rejected to intercooler per minute mkp T2 prime minus T2 k kilojoule. M is equal to mass of air compressed per minute. Kp is equal to specific heat of air at constant pressure. T2 prime temperature of air before entering the intercooler. T2 is equal to temperature of air after leaving the intercooler. Ideal intercooler pressure, it may be noted from this that savings in work increases as intercooling is increased. When intercooling is perfect, that is when air is cooled to intake temperature in the intercooler point 2 lies on isothermal curve, and there is maximum savings. In this case, work required varies with the chosen intercooler pressure P2. When the initial pressure P1 and final pressure P3 are fixed, the best value of the intercooler pressure P2 shall be fixed to give minimum work. This value of P2 can be found by differentiating pressure of W with respect to P2 and equating it to 0. The equation can be rewritten by putting n minus 1 by n, that is equal to y. W is equal to constant into P2 by P1 y plus P3 by P2 y minus 2. Differentiating and equating it to 0 for minimum work, dW by dP2 equal to y P2 to the power y minus 1 by P1 to the power y minus y into P3 to the power y by P2 to the power y plus 1 equal to 0. Dividing through by y and rearranging P2 to the power y minus 1 by P2 to the P1 to the power y equal to P3 to the power y divided by P2 to the power y plus 1. Therefore, P2 to the power y plus 2 P2 to the power 2y equal to P1 P3 to the power y. So taking y root of throughout both sides, P2 square equal to P1 P3 or P2 by P1 is equal to P3 by P2. P2 is equal to root over P1 P3. This shows that minimum work requires or maximum efficiency. The intercooler pressure is the geometric mean of the initial and final pressure or pressure ratio in each stage is the same. This equation gives the best value of P2 when P1 and P3 are given for minimum work or maximum efficiency. Minimum work and maximum efficiency. Minimum work required per cycle, so that is equal to W equal to 2 divided n into n by n minus 1 P1 V1 P2 by P1 whole to the power n minus 1 by n minus 1 joule. That is the minimum work required per cycle. P2 by P1 equal to P3 by P2. So P3 by P1 whole to the power 1/3 is equal to P2 by P1. Minimum work required per cycle in terms of P1 and P3, W is equal to 2 n by n minus 1 P1 beyond P3 by P1 whole to the power n minus 1 by 2n minus 1 joule per cycle. Minimum indicated power of the compressor W into n by 60 joule per second or watt. Okay. Last, if you like my video, you have to subscribe. Okay, thank you.